Okay, I think I can start welcoming you all while we wait for the last few people to enter the room. So welcome to this week's Landscapes Live seminar. My name is Vivi Petersen and I'm chairing the seminar today. And then we have as well Pierre Valla and Michael Benrails as moderators. And today we are lucky to have Andrew Christ here from the University of Vermont. And I guess you still classify as early career, Andrew. And Andrew, he did his PhD at Boston University, finishing in 2019. And now he's been at the University of Vermont since then. And the title of Andrew's talk today is Greenland's Warmer Past. And after Andrew's talk, you're welcome to ask questions, and you can also add comments in the chat during the talk. And after the talk, you're also welcome to raise your hand in order to use the microphone. Then we can ask you to unmute and you can ask your question. So I think that's the only practical things we have to tell you now. And I think I'll just then give the word to you, Andrew.
Great. Thanks so much for inviting me to give a talk here today. And I'm just really excited to be able to share the work that I've been working on with a great group of people over the last couple of years across such a wide audience. So the title of my talk today is Camp Century Revisited, an Ecosystem Under the Ice Reveals Greenland's Warmer Past. And before I get too far into talking today, I just want to acknowledge that much of the work that I'm presenting here today is just the product of a really great collaborative team who have shared their time, resources, and expertise on building this data set from this really unique climate archive from the very first ice core at Camp Century. So before I start talking about science, you can't begin to discuss Camp Century without understanding its history. And the way that I want to start today is by talking, kind of centering ourselves about where we are in the present. And we all know that climate change is really the existential threat of our time. And so most recently, we are above 410 parts per million. And this is quite a change even within my lifetime. I was born at 355. And then if we go back to the very beginning of the record when my parents were born, at 318 parts per million, we see just this incredible change in Earth's atmosphere that we are responsible. And so while today we now recognize climate change as this existential threat, 60 years ago, humanity was facing a very different existential threat. And that threat was nuclear war between the United States and the Soviet Union, because the Arctic Ocean was the closest path between the two superpowers. There was quite a worry that there would be missile strikes shot across the Arctic Ocean. And so the fear of all-out nuclear war between these superpowers led to militarization in the far north. The NATO nations, which were allied against the Soviet Union at that time, were building military installations far above the Arctic Circle. And the United States, with Denmark's permission, built a missile detection warning system at Thule in northwestern Greenland. And the US military was doing things at that time that were seemingly science fiction. And the one that is probably the most outlandish is Camp Century. So now I'm going to show a old US Army propaganda video introducing this place. Oh, I'm not sure that the sound is playing, but it is this. Can someone tell me if the sound is playing? Sorry.
Yeah, unfortunately, we're not hearing anything.
Oh,
Do you want to swap to YouTube instead, or?
Yeah, 1 second. Let's just try that. Sorry for the technical difficulties, everyone.
Oh, don't worry about it.
Oh. How did that work?
We still don't hear anything. Maybe if you stop sharing your screen, and when you share your screen, then you have
Can you
to
hear this?
click a box. No, we don't hear anything.
All right, well, this is a old map. I guess I'll just explain it then. There's this kind of funny sounding mid 20th century American propaganda video where he's talking about this camp, this military installation built inside of the Greenland Ice Sheet, only a few hundred miles from the North Pole. And the island of Greenland has this massive ice cap on it that is a mile thick below Camp Century. And the rest of this video is really talking about how they built this base, which involved bringing everything up on snowcats up to the surface of the Greenland Ice Sheet and building this insane place. And they tell the story of Camp Century, the city under ice. All right. One second. And Camp Century was sold to the public, very publicly, by the US military as this Arctic research laboratory. And they brought in media to showcase just how advanced the US military was at adapting to really challenging conditions in the Arctic, as well as trying to showcase our scientific capabilities as well. And so, you know, this place was very visible to the public in the Western world with articles in National Geographic. And then I'm just going to show a couple more clips from that video where they also showcase what they were doing to have fun, which involved this sort of ridiculous jerry-rigged oil canister where they did a bucking bronco thing. And they also wanted to show that this was a comfortable place to live. You were living inside of prefabricated buildings in these ice tunnels and getting to eat steak. You know, it was very different from the previous images of working in Greenland or in Antarctica, where Scott and Shackleton and Amundsen are kind of at wit's end eating whatever they could. But this was shown to be much more comfortable and modern. And so it leads into this sort of, you know, science fiction feeling about this place. And I mean, it's kind of interesting to look at pictures of Camp Century and think of maybe how this place permeated into popular culture in other ways, because these ice tunnels from this military installation look very similar to some images from the Star Wars movies. Camp Century was built at the apex of the atomic era. And so this place was actually powered by a small nuclear reactor. And so later in this propaganda video, they show them activate this reactor for the first time. And it was enough electricity or energy to supply electricity for almost 100 soldiers and engineers working at Camp Century. They also brought a couple of Boy Scouts, one from the US and one from Denmark, to live at Camp Century for an entire summer, which apparently, if you read some of their accounts after the fact, it was pretty difficult for those 17-year-old boys living up at Camp Century. And then they also managed to get Walter Cronkite, the famous CBS News anchorman, to come up to Camp Century and film an extended newsreel about this sort of science fiction military base built in the Greenland Ice Sheet. And Cronkite has this amazing quote at the end of his newsreel: "Man brought his greatest scientific achievement, power from the atom, to the very top of the world. But can he live here? can he stop the crushing force of the ageless ice? Well, the other thing that was going on, not just showing whether or not the US could make this base, was that they were devising if it was possible or feasible to store and hide nuclear weapons inside of the ice sheet itself in this operation called Project Iceworm. So the crushing force of the ageless ice was unfortunately too much to bear for Camp Century, because as we all know, ice sheets flow through deformation. And so these ice tunnels, which had been built in the surface of the Greenland ice sheet, started to move in over time and collapse, kind of like the trash compactor in Star Wars. Now, the other problem is that this part of Greenland received a lot of snowfall. And so these structures were starting to collapse from the weight of the overlying snow that was being deposited year after year. And so these pictures are from a trip back to Camp Century a few years after it closed in the mid-60s to show what had happened. And so the US military very quickly realized that building and maintaining military bases inside of the ice sheet and then trying to store any weapons inside of them was a terrible idea, because they would ultimately be destroyed by the ice. But one of the more important legacies of Camp Century is that we have discovered that ice sheets are great archives of paleoclimate data. And that is because at Camp Century, one of the science experiments that they were conducting was the drilling of the first deep ice core. And the Camp Century ice core was the first that was ever drilled through the entire thickness of an ice sheet and actually penetrated into the subglacial landscape. And this ice core really revolutionized our understanding of paleoclimate over the last 100,000 years, because for the first time, we were able to see a very detailed atmospheric record of Earth's climate from the Holocene into the last glacial termination, the entirety of the last glacial period, and the abrupt climate changes that occurred during interstadials, and back into the last interglacial period. At the bottom of the Camp Century ice core, they recovered basal ice materials, about 16 meters of debris-laden ice or silty-rich ice. And then at the very bottom of the ice core, about 3.5 meters of frozen sediment. While the ice core itself was studied intensively after its collection, these basal materials were not studied very much. And then they were actually more or less misplaced in a freezer for several decades. And what has happened instead is that a few years ago, at the ice core storage facility in Copenhagen, J.P. Stephenson and Dorte Dahl Jensen were spearheading an inventory of all of the ice cores in their freezer, and they came across these cookie jars, these scientific cookie jars that had frozen dirt in them. And it had these faded labels on them that said Camp Century sub ice. And they realized that this was the Camp Century basal sediment. And so they assembled a team that I was very fortunate to be a part of through my postdoc advisor, Paul Bierman, to try to analyze the sediment using modern techniques that were not available at the time of its collection back in the 60s. So it's pretty incredible to be able to look at these sediments, so many decades after they were originally collected, and thankfully stored and preserved really well in the freezer. And so this story of Camp Century is not just a city under the ice. We have learned that it is really a story of the ecosystem or fossil ecosystem under the ice, because we found in the sediment fossil plants and biomarkers from ancient tundra from at least 2 ice-free events, once in the early Pleistocene and another in the last 1,000,000 years. And we have some new data that may tell us when that was. This Camp Century subglacial sediment is really a time capsule, because it tells us a tale of a warmer Greenland when the ice sheet was smaller than it is today. And of course, this is important for us to understand as humanity continues to burn fossil fuels and rapidly warm the polar regions, especially in northwestern Greenland. This is important to understand because as the Greenland ice sheet melts in response to climate warming, we could see the margins of the ice sheet begin to melt away and contribute to sea level rise. Camp Century is actually in a particularly important place because it is near one of the margins of the ice sheet that is melting most rapidly today. So to understand the future of the Greenland ice sheet, we can look to the geologic past. And specifically, we want to know, when did parts of the Greenland ice sheet melt away in the past? There's a big complication, however, in understanding that geologic record, is that the present ice sheet covers most of the Greenland landscape and has eroded archives that formed in formerly ice-free landscapes. And so ultimately, we have a very incomplete and fragmentary geologic record of the Greenland ice sheet over the last several million years. And so in order to understand what has happened to the Greenland ice sheet through geologic time, we have to look to other climate archives. The deep ocean supplies the longest record of ice sheet behavior by looking at the flux of ice rafted debris from marine terminating glaciers, as well as paleoclimate proxies recovered in marine sediments. There are also geophysical analyses or mapping of the continental shelf surrounding Greenland that tell us about the past advanced history of the Greenland ice sheet over the Pleistocene. And we can also go to coastal areas of Greenland where there are older geologic deposits that contain fossils, such as at the Copenhagen area in northeastern Greenland, which has boreal forest remains with ages that could be in the late Pliocene to possibly the early Pleistocene. So what we've learned from these longer term geologic records of the Greenland ice sheet is that we have an ice sheet that is largely persistent throughout the Pleistocene, but dynamic, capable of expanding and contracting. We can then go and look at the bottoms of ice cores to learn more about this geologic history. And so when we compile the offshore and ice core basal material geologic records, it looks like the Greenland ice sheet must have been smaller at some point within the last 1.1 million years. From marine records, which provide generally better age control and continuous climate records, we are beginning to see the picture of the Greenland ice sheet, how it responds to glacial interglacial cycles. And at least in southern Greenland, marine sediments, specifically pollen concentrations and changes in sediment composition, suggest that southern Greenland was ice-free and forested during MIS 11, 400,000 years ago. The disadvantage to marine records is that they are ultimately indirect measures of former ice sheet extent. We don't know just how small or large the ice sheet was for most marine records. On the other hand, we have ice core basal materials, which can directly record the past presence or absence of the ice sheet at the locations of those ice cores. But it's been really challenging to get good age constraints and interpretations of those ice core basal materials. But what we see so far from them is that at least in southern Greenland at Dye 3, the discovery of boreal forest DNA, ancient DNA, suggests that that part of Greenland had boreal forest on it at some point between 450 to 800,000 years ago. In the interior of Greenland near the ice sheet summit, the GrIS ice core has basal ice age constraints of 950 or 970,000 years, suggesting that that part of Greenland has been ice covered since that time. Nearby at GISP 2, the subglacial bedrock beneath the ice sheet must have been exposed within the last 1.1 million years, at least once and potentially more times. The flip side to that, which I guess exposes how difficult it is to interpret these ice core basal materials, is that the silty ice above that bedrock shows persistent ice cover and non-erosive conditions for most of the last 2.6 million years. So this is all to say that precise age constraints of ice-free events from terrestrial records in the bottoms of the ice cores remain elusive. So this is where Camp Century comes in. And so now I'll explain what the Camp Century sediment is and what we did to understand it. So this subglacial sediment contains 2 units of diamectin separated by a sediment-rich ice layer, an upper diamectin and a lower diamectin. And in our pilot study, we have examined the very uppermost sediment just below the ice sediment interface, sample 1059-4. And I'll use these same colors throughout the talk so that you are visually cued to understand which unit I am talking about. And a lower diamectin 1063-7 from near the very bottom of the subglacial sediment. Both of these are poorly sorted homogeneous diamectins. They are rich in many different, in a lot of quartz, which is important for some analyses that I'll explain in a little bit. But the upper diamectin was slightly more coarse in grain size than the lower diamectin, which was more rich in clay. So what did we do? And what am I going to walk you through on our analyses of this Camp Century sediment? First, I'll explain our evidence for ice-free conditions using pore ice stable isotopes and macrofossils and biomarkers. And I'll talk about our age constraints on this sediment, which include cosgenic nuclide burial dating, as well as luminescence dating. I'll talk about the weathering history of the sediment and its provenance by looking at different weathering products in the sediment, as well as multiple geochronometers that tell us about provenance. And then, if Camp Century is ice-free, we want to know how much ice did Greenland lose in the past. And we do this by doing some ice sheet modeling to get a minimum sea level contribution from Greenland such that Camp Century is ice-free. So what evidence of ice-free conditions does this sediment contain? Our first line of evidence is that the pore ice water-stable isotopes are enriched relative to all the overlying ice and modern precipitation at Camp Century. So the Delo 18 of modern precipitation at Camp Century is -29 per mil, and the pore ice Delo 18 values from these 2 sediment samples are highly enriched. If you plot those values against the profile of all of the Delo 18 measurements from Camp Century, we see that they are values that are highly enriched, far beyond anything that was measured previously. And so if you were just to interpret this as a temperature change, we would see values of over 8.5 to over 10.5 degrees centigrade warmer than present. That does not make sense because that is too warm of conditions for precipitation to fall at Camp Century's current elevation of almost 1,900 meters. There couldn't be an ice sheet with those warmer temperatures. So we interpret these enriched stable isotope values due to a net elevation lowering effect, as well as slightly warmer temperatures. So this is a very schematic cartoon of what I'm going to explain, but presently we have precipitation with a Delo 18 value of about -29 per mil, falling on a ice sheet surface at around 1,900 meters over an ice sheet that is almost 1,400 meters thick, with bedrock presently around 500 meters. Of course, the Greenland ice sheet is isostatically depressing the crust. So if you were to remove the ice sheet, glacial isostatic adjustment would raise the elevation of the underlying bedrock, resulting in a net elevation lowering of where precipitation falls. So if you remove the ice sheet and the crust rebounds 450 meters, you would see an elevation lowering of 940 meters. That accounts for most of the enrichment in the Delo 18 measurements we have, with an additional enrichment due to slightly warmer temperatures, 0.2 to 3 degrees C warmer. This is all to say that these enriched pore ice Delo 18 values require precipitation at lower elevations that imply ice-free conditions. The second line of evidence for ice-free conditions in northwestern Greenland and preserved in the sediment was that we discovered tundra macrofossils as well as leaf waxes underneath 1.5 kilometers of ice. And this really was one of the most exciting days of science I have ever had, because we were in the lab, Paul Bierman and I, and our undergraduate assistant, Landon Williamson, and we are sieving the sediment to prepare it for other analyses. And as we are sieving the sediment, we see these little black specks floating around in the rinse water. And we were all kind of like, what is that stuff? And got a pipette and then put it on, sucked a little bit up and looked at it under the microscope. And we saw a twig, and it was just totally exciting because we had no idea to expect that. And so it was really a eureka moment, because we spent the rest of that afternoon looking through this sediment and just finding as many little pieces of macrofossils as we could. I am not a paleoecologist, and so to me, I did not really know what I was looking at that time. And so we have worked with several different paleoecologists to help us understand this biologic record. Dorothy Petit from Lamont Doherty looked at the macrofossils and found mosses and leaf tips and twigs, as well as fungal spores that resemble modern Arctic tundra and from ice-free areas of Greenland. The leaf waxes that are in this sediment resemble modern Greenland shrubs that are found in ice-free areas of Greenland today. And Elizabeth Thomas at University at Buffalo did those analyses. And then just one thing to point out is that we have slightly better preservation of these macrofossils in the upper diamicton, and there's a greater abundance of them as well. We did take one twig and radiocarbon date it just to see possibly how old the sediment is, and it yielded an infinite radiocarbon age, meaning the sediment is older than 50,000 years. The main characteristic of these macrofossils that we found is that, when I was looking at this stuff under the microscope, it was just sort of like hash of woody tissue. And I didn't know what that was. I could tell that it was plant material, but it was not possible for me to identify it. And so we've been working with Barry Rock from University of New Hampshire, who has looked at some of this woody tissue under a scanning electron microscope. And from looking at a cross-section of the tissue, he's been able to identify that this is salix, or Arctic willow. So the next question we want to answer is, how old is the sediment? So the first way that we do this is using cosmogenic nuclides, beryllium-10 and aluminum-26, that are produced in quartz in the near surface. These two different nuclides have a production ratio at the surface between 6.7 and 7.3. And these two nuclides are radionuclides with different half-lives. So we can use this trick of the ratio at which they're produced at the surface and their different decay rates to understand the burial history of sediment. Because if an ice sheet advances over that landscape, nuclide production stops, and then the nuclide inventory begins to decay at those different rates. And that initial ratio of aluminum to beryllium begins to decrease. From that, we can determine a maximum duration of burial. These radionuclides with different half-lives constrain our burial history. And this is a 2-isotope plot that is commonly used in cosmogenic nuclide dating, where if a sample remains at the surface somewhere, it's going to accumulate more and more beryllium-10 aluminum-26 over time at a consistent ratio of about 7.3 in Greenland. But if buried, production stops and aluminum begins to decay more quickly than beryllium. And so that ratio decreases over time. These are not absolute depositional ages, but we can get isochrons that tell us the total burial history, which gives us a way of saying sediment must have been exposed within that time. So what does the data from Camp Century look like? Well, we have multiple grain sizes in these two different samples from the upper and lower diamicton that have very different burial histories. The upper sediment has an aluminum beryllium ratio of about 4.5 that corresponds to total burial no longer than 1.0 plus or minus 0.1 million years. The lower sediment has a much lower aluminum beryllium ratio of 1.8, which means it has been buried much longer, but no longer than 3.2 plus or minus 0.4 million years. So we have evidence for at least 2 ice-free periods at different times in the sediment. The other way that we can figure out the burial age of the sediment is using luminescence dating. And I know this is a group of geomorphologists, so some of you may know the details of luminescence dating better than others. This is still pretty new to me, but I think it's helpful to explain what luminescence dating is. And that tells you when sediment was last exposed to sunlight. So the way that this works is that when sediments are buried beneath Earth's surface and shielded from sunlight, the background radiation from other materials in the soil or sediment will begin to radiate out and excite electrons and other minerals in the crystalline lattice. And the electrons that are excited by that fill in the holes in the crystalline lattices of minerals like quartz or feldspar. And so over time, you build up a luminescent signal as those electrons accumulate. But if the sediment is exposed to sunlight, you reset this clock and those electrons are bleached out and you reset it in a very short amount of time. But if that sediment becomes buried again, the electrons begin to accumulate from that low-level background radiation. Some minerals, like feldspar, lose a little bit of those electrons that had accumulated through time, and we call that fading. So us as geologists can go and collect samples in the dark and then capture this luminescence age of those electrons that had accumulated in those holes of crystalline lattices over time. If that wasn't clear, it is kind of like if you were to wear the same shirt for a month. Over time, it would accumulate stuff from the environment, dirt, smell, whatever, and you'll accumulate sort of a stinkiness signal. But if you put that shirt in the washing machine, it's going to get clean in a very short amount of time, right? So now let's talk about our age constraints. The lower diamicton is much older. The aluminum beryllium burial age has a maximum age of 3.2 plus or minus 0.4 million years. And the infrared luminescence age of feldspars has a last light exposure age of greater than 0.7 million years and probably more than 1.4 million years. These age constraints on the lower diamicton suggest that it may record an early advance of the Greenland ice sheet. Because from geophysical records as well as ice rafted debris records from surrounding Greenland suggest that the Greenland ice sheet first achieved its full extent about 2.6 million years ago. So this diamicton could have been formed through an early advance of the Greenland ice sheet. And the macrofossil material as well as biomarkers in the sediment could represent the oldest record of vegetation recovered below the ice sheet so far. Now let's talk about the upper diamectin. And I'm first going to focus in just on the cosmogenic nuclide maximum burial age of less than 1.0 plus or minus 0.1 million years. This additional age constraint fits with pre-existing data from other ice cores around Greenland that suggest there are no age constraints greater than 1 million years, meaning that the ice sheet must have melted and reformed at least once within that time frame. So within this graph here showing all of the age constraints of the other basal materials from the deep ice cores, we see that there's nothing greater than 1 million years. And then one record that I want to compare specifically is that the aluminum beryllium burial ages at Camp Century in that upper diamectin, as well as the subglacial bedrock from GISP-2 are very similar and both require exposure within the last 1 million years. So these two distant sites between the northwest margin of Greenland at Camp Century and GISP-2 in the interior of the Greenland ice sheet below the present summit both have maximum burial ages of less than 1 million years or so, suggesting that the entire ice sheet must have been largely absent within that time frame. Now let's talk about the infrared luminescence dating that we have on the upper diamectin. And this is some new data that we are working on. And what we did is we went back to the sediment archive in Copenhagen to cut an additional sample of the upper diamectin in the dark and red light, and then wrap it in aluminum in foil and transport it to Utah State University, where Tammy Rittenauer processed these samples in red light to prevent any inadvertent exposure to sunlight. And what Tammy did is she used replicated infrared luminescence dating of multiple aliquots, meaning multiple grains in those two different sediments, using in that sediment using two different grain sizes to get IRSL ages. And we see that we have very coherent IRSL ages using multiple aliquots. Nearly all of the aliquots produced meaningful data, which have uncorrected IRSL ages of about 290,000 years. We also collected fading measurements on the sediment to see if a fading correction was required for the sediment. And when we apply the measured fading rate to those uncorrected ages, we get fading corrected IRSL ages of about 391,000 years. Regardless of the fading correction, these upper sediment IRSL ages require exposure within the last 420,000 years. And we think that this is a robust data set because we have very coherent IRSL ages. We have measurements in two grain sizes from the same sediment, multiple aliquots in each grain size. And we don't see evidence of partial bleaching in any of these grains. And the coherence of those IRSL ages suggests that it's a single sediment source, meaning that we are not having grains that have completely different sunlight exposure histories. So what do these exposure ages line up in terms of paleoclimate? So if we plot the raw IRSL ages without a fading correction, they correspond to the middle of the marine isotope stage 8 glacial period. Now, it doesn't really make sense for this part of Greenland to have been ice-free and exposed during the middle of a glacial period when presumably the ice sheet was in an expanded state. But if we consider the fading corrected ages, they slightly postdate the peak of the MIS-11C interglacial about 400,000 years ago. So if we consider the fading corrected ages, they correspond with climatic cooling after the MIS-11C interglacial period. On the right here, I am showing a bunch of different paleoclimate indicators. And at the bottom is the fading corrected IRSL ages. And we can see that they correspond to growing global ice volume from the benthic Deloy team stack, falling global sea level, falling carbon dioxide concentrations, as well as correspond to an increase in the flux of ice raft debris offshore of Greenland that could correspond to an expansion of the ice sheet, as well as cooling sea surface temperatures and land temperatures, as well as a decline in pollen concentrations off of southern Greenland. So these IRSL ages from the Camp Century Upper Diamicton actually record the readvance of the ice sheet as climate cooled in burial following that ice-free event. We can use the IRSL ages to further inform our aluminum beryllium burial history, which, if you remember, is just a total burial history. So what we did is we corrected these aluminum beryllium measured values from the upper and lower Diamicton and corrected them for an additional time of burial using that fading corrected IRSL age of 391,000 years ago. If you account for that burial, it slightly raises the aluminum beryllium ratios of both sediments, giving us the aluminum beryllium ratio at the time of burial following that last ice-free event. In the upper Diamicton, we can then apply a variety of different exposure durations during that ice-free event to get a maximum duration of exposure. Because if you expose the sediment for too long, you end up with an initial starting value that is a non-real solution. So what we found from that modeling experiment is that you cannot expose the upper sediment for any longer than 14,000 years during the last ice-free event. We then also corrected for the additional burial of that lower sediment, assuming that it was not exposed during MIS 11. And we can see that these two sediments had sort of a similar incoming burial history at the beginning of that last ice-free exposure event, possibly during MIS 11. Less than 14,000 years of ice-free exposure in Northwest Greenland during MIS 11 aligns with some sea level reconstructions from that time. Two different sea level reconstructions bracket the duration of higher sea level above modern between 17,000 years or 11,000 years. And so that 14,000 year exposure duration in Northwestern Greenland could make sense. So we also want to know what the weathering and transport history of this sediment is. And I want to go back to the aluminum beryllium modeling that we have done, because I think it suggests something important about where the upper sediment came from. As I alluded to in that previous graph, if we exposed the upper Diamicton for as long as 14,000 years during that last exposure event, it would have had an incoming inherited 2610 aluminum beryllium ratio, very similar to the incoming aluminum beryllium ratio of the lower sediment 1063-7. And so what this suggests is that the upper Diamicton was sourced from material very similar to the underlying sediment like 1063-7. And we did a series of different geochronometric analyses on multiple mineral phases in this sediment to understand the provenance of the upper and lower Diamicton. And in each of these different geochronometric analyses, whether it's apatite helium ages, hornblende argon ages, or zircon uranium lead ages, we see that there is no significant difference in the age populations between these two, between the upper and the lower Diamicton. What that first suggests is that we did not have a major change in ice flow direction between the units, which would have brought in grains with a very different provenance. But what it also supports is that the upper Diamicton is sourced from local material similar to the lower Diamicton. It has the same minerals in it. Both samples have very similar mineralogy, especially with regards to bulk mineralogy. But if you look at the heavy minerals, they're slightly different. there's a different proportion of amphibole and pyroxene and garnet in the upper and lower samples. And this could suggest different weathering histories of these two different sediments. And we have seen a similar trend looking at secondary weathering products in the Camp Century sediment, where the upper diamectan has very low pore ice major ion concentrations relative to the lower sediment. And we also have a different amount of weathering clays on these two different units. And so these differences in heavy minerals and the secondary weathering products suggest that there was more chemical weathering of the upper sediment and removal of those secondary weathering products, just a different weathering history. So let's synthesize what I am talking about here in one possible schematic glacial history. And I'm using this really cool MATLAB program by Chad Green to show the bed map of Greenland. And so sometime in the early Pleistocene, we had an ice-free event where there was tundra growing and permafrost, possibly some lakes. And then there has been persistent but dynamic ice sheet cover over this part of Greenland through the Pleistocene, where this lower diamectan became entrained. Then within the last 400,000 years, possibly MIS 11C, there was an ice-free event where a tundra ecosystem emerges. That ice-free event lasted no more than 14,000 years. And that older local glacial sediment, similar to the lower diamectan, is exposed and further weathered. And then the ice sheet has re-advanced and covered northwestern Greenland, potentially for 400,000 years. If Camp Century is ice-free, how much ice does Greenland lose? Benjamin Kiesling has been doing some ice sheet modeling to answer this question. And what he has done is made an ensemble of ice sheet models by varying several different parameters. And in the ensemble of 96 unique simulations, 79 simulations result in the deglaciation of Camp Century. So what we want to understand is just how much smaller is the Greenland ice sheet to exposed Camp Century. And so if we take the most conservative simulation, where Camp Century is just barely ice-free, we see that the Greenland ice sheet must have contributed 1.6 meters to sea level rise. It could have been more, but this is a hard lower limit. So the big takeaway is that the Camp Century sediment provides direct evidence for two ice-free events in Northwest Greenland. We know there are fossil ecosystems preserved beneath the Greenland ice sheet. The Greenland ice sheet appears to have been quite resilient during the Pleistocene, surviving most interglacials, but there has been at least one major ice sheet retreat within the last million years. Northwestern Greenland has been deglaciated within the last 400,000 years, possibly during MIS 11C, for no more than 14,000 years. And if Camp Century is ice-free, there must have been a contribution of at least 1.6 meters of sea level from Greenland. And I'll end today with a question: was the duration of MIS 11C key to the retreat of the Greenland ice sheet? MIS 11C was very long relative to other Pleistocene interglacials, 29,000 years. And so while the climate forcing factors that caused the ice sheet to retreat during MIS 11 are very different from what we face today with higher carbon dioxide in the atmosphere, what I am suggesting or proposing is that the duration of very long temperatures that we will see from high CO2 could be bad news for the Greenland ice sheet, right? So even under the moderate RCP emission scenario 4.2, it'll take 30,000 years to get back to 350 parts per million CO2 in the atmosphere. So if we create a climate that is warm for a very long period of time, will that mean that the Greenland ice sheet melts again? I hope not. And I'll end today just saying that we are looking for a master's student to help us with the remaining archive of the Camp Century sediment. I'm actually going to Copenhagen next week to help cut the remaining samples, and I'll bring it back, and we will need help from a master's student to work on the chemistry here at UVM. So I'd be happy to take any questions, and thank you all for coming to my talk today.
Thank you so much, Andrew, for this very interesting talk. And the chat is open for questions and comments from everyone. And I guess while we wait, I can just ask you a question. So it's amazing to me that there are only these two. I mean, why do you think, what makes them so special, these two periods of time?
So yeah, that is a good question. Now, this is sort of the question of like geologic preservation of things, right? Is that we don't know what has been eroded or if material has been eroded. So it is possible that there may have been other exposure events that, had sediments, but they've been eroded by successive ice sheet advances. I can't say that for sure because we don't have any evidence of that in the sediment. So maybe there are more and we just don't know about them. Or maybe it is the sort of most conservative idea that, no, these are really the only ice-free events that are preserved here. So it's hard to say just because, again, these are just time capsules. So it's like, the time capsule in your town or something where you find the one from 1930 and then there's another one from 1850. And, obviously stuff happened in between, but that's all you have to look at.
Yeah, but in your modeling of the cosmogenic nuclides, have you tested the results if there had been actually erosion of some younger sediments on top?
Right. So the next phase of this project will actually help us figure that out. Because right now we just have these two horizons of measurements, but what we will end up with is a depth profile. And the profile of those aluminum beryllium measurements could tell us if this was if the upper diamectan really is one sediment with a profile that declines with depth that would give us a better understanding of its burial history, or there could be multiple profiles within that sediment. We don't know yet. And that is one of the main questions that we're trying to address with the additional analyses of the sediment.
Thank you.
Thanks.
So can I take over? There's no question in the chat, but I may have a question for you, Andrew. Well, thanks for the very nice talk. I have a question about the provenance of these quartz grains that have been, or feldspar grains that have been used for luminescence dating. Have you looked at the quartz? What is the origin of the material? If these are like fluvial sediments or aeolian sediments or purely glacial sediments? I know that if you look at SEM images, you can see more or less some specific type of erosion, abrasion forms on the quartz grains. Have you looked at this?
Yeah, great question. So so I'll answer it in a couple of ways. First, we did try OSL dating on the quartz, but this is a little bit outside of my expertise because I'm not an OSL expert, and Tammy would know. But this quartz is not mature enough for using OSL on it, so we can't use it quite yet for that. But to answer your second question about its provenance, there was one of the few papers that was written about this subglacial sediment from Camp Century was an SEM analysis of the grains, and there's a bimodal distribution of the quartz grains that about half look like they're subglacially abraded and the other are rounded aeolian grains. Pioche Blard has done some more SEM analyses of the grains to investigate it further using an SEM that is not from 1970. And he has found a very similar result. And so, yes, it looks like there's a mixture of different origins here. But when we did these cosmogenic nuclide analyses, we were using, I didn't separate them out by grain shape because I've tried that experiment in other settings and it doesn't work. But we did do it in multiple grain sizes, and the coherence of those exposure histories, the coherence of the aluminum beryllium measurements in both of those sediments is so similar that I think we are capturing a similar burial history.
Okay, thanks.
Thanks, Pierre.
Tammy answered also in the chat that the quartz was saturated, so well beyond the range of dating for luminescence. Thanks, Tammy.
Thank you, Tammy.
So do we have other questions? Then feel free to put them in the chat or raise your hand. Then we can ask you to unmute. That's also a possibility.
Okay, I have another question, if there's not other, about the vegetation macro rests that you found in the sediments. You talked about the fact that some of the species were kind of equivalent to modern species that we found on the deglaciated part of Greenland. Was there any possibility that like a very efficient wind at the time of similar situation as today, like only the outside of Greenland was deglaciated and that can transport this vegetation over long distances?
Yeah, so yes, the question of whether or not these are wind transported macrofossil materials, that is a good point. But I think there's good evidence that this sediment is not aeolian sourced. And I think, first of all, that is because it's within this matrix of subglacial as well as aeolian sediments that I think we're forming in that ice-free landscape at the same time with and supporting that tundra ecosystem. And I know that this isn't direct evidence that I can link to this study, but there is radar data from northwestern Greenland that suggests there's actually a large lake basin that may fill in with water during ice-free periods. And so I guess what I'm envisioning here is, yes, I mean, like, we don't know how much smaller the ice sheet was, but I think that it is good evidence that these tundra fossils are not from very far away. Does that help answer your question?
Yeah, thanks.
Thanks, Pierre.
Okay, I think there is a comment in the chat, but I think it's mostly for Pierre. Yeah, so we have also Nikolai Krogh Larsen that has raised his hand, so I'll just unmute Nikolai.
Okay, thank you very much. Now I'm unmuted. Thank you very much for a nice talk, Andrew. It's very interesting. I remember that the people or the researchers at GrIS, they looked at the silty ice above some years ago, and they also did some luminescence dating, and they got an age of approximately 600,000 years on the silty ice on numerous samples. How does that fit into your results? Is that because the ice sheet, when it re-advanced and trained older sediments, or does it mean that the ice would be older than 600,000 years?
So that, I mean, yeah, I have not seen this data set of these luminescence ages in the basal ice. But, I guess because at least in this sediment, we see so many grains with coherent IRSL ages that I think that this sediment is, sourced from that specific ice-free event. But there could have been entrainment of sediments somewhere else that brought it into the silty ice. But I have not gotten to see that data set. And so I'm not sure how much I can interpret it yet or relate it to what we see, but what you suggest may be a possibility.
Okay. I don't know if you have any, Nikolai, I don't know if you have any more comments.
No, that's fine. Thank you.
Good.
Thank you, Nikolai.
Yeah, because I was actually going to ask myself if there were any materials in the ice above, but now we hear that there are some. Because I guess that could give an indication also about how much erosion there's been. Do you
Yes,
know
yeah.
about the contact between, so your sediments, I mean, I guess you have ice in your sediments and then you have ice just above the sediments that is ice. So how do you make that distinction then?
Between like what is the actual contact is, it is the sort of concentration of ice versus sediment, and also the density of those different parts of the core. And above the uppermost sediment sample that we looked at, it is definitely ice with lesser amounts of sediment in them. And the basal ice, there is some work on earlier work back in the 70s and early 80s that looked at the basal ice to try to understand where it came from. And from those initial studies, it looks like the sediment is sourced subglacially, not necessarily from the sediment underneath this part of the core, but maybe somewhere else. And that is another project that is upcoming as well. And so when I am going to come help cut the sediment samples, we are also cutting the basal ice samples to do analyses on those and give them the full treatment. And one thing that I'm excited to, hopefully contribute with that basal ice project is that how do we compare our cosmogenic nuclide measurements in the basal ice and the lower sediment. And I think that by doing a similar tests as what we've done in the sediment to that ice, or the sediment in the ice, that we'll be able to link them more carefully, and as you suggest, understand the erosional processes, because that is the part that has been difficult to ascertain just so far.
Good. Thank you so much, Andrew.
Yeah.
And it seems like there's no further questions in the chat, and we also past 5 o'clock. So I guess it's a good time to close the seminar down, and hopefully we'll see all of you again next week. And yes, again, thank you, Andrew.
Yep. Thank you all so much for organizing and for having me here today, and your good, thoughtful questions. I really appreciate it.
Good.